So in this video, we're going to talk about shapes of graphs, and in particular, we're going to talk about the property of concavity. Let's start with a specific example. Let's say that we have a ball that's been thrown up in the air. So this is a graph of the path of the ball, where this is time and this is height. And notice that as we throw the ball starts out, because it was thrown up, by increasing along this side of the graph, right? Our function, I'm coloring this in purple. Maybe it just looked like black in the video. That's okay. So for this purple section, the left half of the graph, we see that our function, f of x, meaning in this case our height, is increasing. But as the ball continues through time, we see that although the height is increasing, it increases at a lesser and lesser rate, meaning that it slows down as it travels up in the air, right? Because gravity's pulling down on it. So that's telling us that the slope of these tangent lines, although they start off being positive, they become less and less and less and less positive until right at the very top where the slope of the tangent line is 0. Let's describe that in mathematical terms. We said that throughout this entire path, our derivative is positive, meaning we have a positive slope, so our derivative is greater than 0, but our derivative is getting smaller and smaller and smaller, meaning that f prime of x is decreasing. And that has nothing to do with the height of the graph, right? That the ball is getting higher and higher in the air. That's different than saying that the rate at which the ball is increasing in height is decreasing, right? The rate of change is decreasing as time elapses. Another way to say this is that our second derivative, the rate of change of the tangent line, is negative. And we have a word for that. That word is saying that because our second derivative is negative, we say that this graph is concave down. I'll write that down here. And our other definition of concave down is that our second derivative is less than 0. That's our technical math way of being able to check whether or not, oops, I'm trying to focus the camera and I'm making it worse. There we go. That looks a little better. What's going on in the second half of the ball's path, right? Things shift after this point right here. This is our critical point. It's where the slope of the tangent line is equal to 0. So this is where our derivative is equal to 0 at our critical point. And for this second half of the path, we see that the height, f prime of x, is decreasing. And by that I just mean that the h values here are getting smaller and smaller and smaller. That's an easy thing to analyze looking at the graph. Our derivatives are talking about the slopes of the tangent lines here, and we can say that our slope always has a negative slope. Oops, I guess instead of saying is negative, to make it match this, that's the same thing as saying f prime of x is less than 0. But notice that our f prime of x is continuing to decrease. Well, it sort of seems like it's increasing, right? Because it's getting more and more and more negative. And I'll even write that down. Is f prime of x is getting more negative. And that's sort of a trick of language, that when we say that something is getting more negative, we do mean that it's getting smaller, right? Because negative numbers are smaller than positive numbers. And so that's the same thing as saying that f prime of x is decreasing. And if our derivative is decreasing, that means that our second derivative is less than 0. So we have some properties that hold for the entire graph. For the entire graph here, we see that f prime is decreasing in both cases, and that means that our second derivative is less than 0 in both cases. So for this entire graph, the function is concave down and the second derivative is less than 0, even though our first derivative is positive over here and our first derivative is negative over on this side. In colloquial language, the way that I like to think of this is that the ball is being pulled downwards. And gravity is a good way to look at this because as the ball is traveling, I give it this initial throw. So it's initially thrown in a direction opposite of gravity, but the entire time that it's traveling, gravity is tugging at it and making the rate of change get closer, pulling it towards the ground the entire time that it travels. And so when I like to visualize concavity, I think of whether or not the object is being pulled downwards or pulled upwards. So this is a detailed analysis of a downward, a concave down graph. Let's do an analysis of a concave up graph. So here's a different function, and for this function, we see that it's concave up, meaning that our second derivative is greater than 0. And visually you can see this by thinking of it's sort of being pulled up the entire time that the object's traveling. And I might think of this like if I'm running with a rubber band attached to my back, and that rubber band, even if I try to run this way, it's tugging at me and it's pulling me so that, and then it snaps back and I get pulled off in this direction. So concave up, colloquially I think of this as being pulled upwards. Even though, again, we have different behaviors in this graph. We see that our derivative is negative here because the derivative of our tangent lines, they're all pointing downwards. So f prime of x is less than 0, even though the slope of these is getting more and more and more positive until right here at the critical point where the slope is equal to 0. That means that the slope of the tangent lines is increasing, meaning that our second derivative is greater than 0. And I'll do an analysis for this other side. In this case, our slopes are always positive, so f prime of x is always greater than 0. And again, we have that our derivative is increasing because it's getting more and more and more positive. So that means that our second derivative is greater than 0. And let's summarize everything that we just said in one simple graphic. I do not expect you to memorize this. I think it's much more important for you to be able to look at a unique graph and be able to analyze what's going on, meaning what's going on with the slope of the tangent lines in each case. That said, I do want to make sure that the summary is clear. I can't fit it all on one screen. But here we see pieces of each of the graphs. If I just saw this one piece of graph right here, I could still say that although the function is increasing, f of x is increasing, and our slope is positive, f prime is greater than 0, we see that the slope is positive, but it's getting less positive as it goes along. That means that our derivatives are decreasing, and we're sort of getting pulled downwards. Again, you can think of this as the path of the ball under gravity, and that although we start off with a positive slope, the slope is leveling off because it's being pulled downwards. The next case that we have is another concave down example. This is where you're traveling down and you're being pulled down at the same time. We have the next two, and these are the final two that I'll break down of the cases of second derivatives and first derivatives. This is a concave up example, but it's one in which the first derivative is negative, meaning my slopes are all negative here, but they're getting less and less negative. They're being pulled towards 0 along this path. And finally, we have concave up, where my first derivative is positive and my second derivative is positive. I'm traveling upwards, my derivative is positive, and my second derivative is pulling me in a positive direction as well. Let's look at an example of this with a graph. Too many papers, sorry. Let's make this look a little better. So here we have a graph, and I want to break up each of the pieces to see what's going on in each place. And we'll notice what are going to be the places where you transition between these 4 different shapes. And we'll call those transition points. These are our 4 different shapes. Clearly, one of the places where we're going to transition, maybe we'll start this right side, because I think this right side is a little easier and will work leftwards. So here we see we have a critical point. And recall, a critical point, that's a place where my derivative is equal to 0, meaning I have a horizontal tangent line. And so we know the critical point is going to break up the pieces of the graph. We see that there's a transition that happens here. The graph is going down, but then it's traveling upwards. And so for this piece of the graph, I'm going to put a dotted line here to indicate that the shape on the left is different than the shape on the right. We have this critical point as our transition point. For this part of the graph, we have positive slopes, and our slope is getting more and more and more positive. We're being pulled upwards. So for this portion of the graph, I can say that my derivative is greater than 0, and I have positive second derivative as well, meaning I'm concave up. You can't quite see that. There we go. Concave up, and I'm being pulled upwards. That's why I know it's concave up, because I feel like I'm being pulled upwards. Let's analyze what's going on this piece. There's something tricky that goes on here, because here it looks like I'm being pulled down, but somewhere in between these two critical points, I start being pulled up again. And just by the shape of the graph, it's hard to tell, but I'm going to pick a point right there. And what happens right at that point? Here, I'm being pulled down, my slope is getting more and more and more negative, but at some point that switches and my slope starts becoming more and more and more positive again. So this point right here is where my slope transitions from decreasing to increasing. And maybe I'll write that down here. And we're going to call that an inflection point. An inflection point is the place where I transition from decreasing to increasing, or from increasing to decreasing, either of those. But technically, what's going on there is that my second derivative is equal to 0 right at this place, right? Because for this part of the graph, I'm being pulled upwards, and for this part of the graph, I'm pulling downwards. So what's the transition from being pulled down to being pulled up? It's right where I'm not really being pulled up or down. It's exactly at 0. So let's look at this next piece of the graph. We're keeping track. So in this region right here, this narrow band of the graph, we see that our derivative is negative, that our slopes are all negative, so f prime of x is less than 0, but we're being pulled upwards, and so our second derivative is greater than 0. The next transition point that we hit is this critical point right here. So let's look at this piece of the graph. For this piece of the graph, my derivative is negative because my slopes are negative, so f prime of x is less than 0. But it looks like I'm being pulled downwards here because my slopes start at 0 and they get more and more and more negative. So that means my second derivative is less than 0. So here my second derivative is less than 0, here my second derivative is greater than 0, and right at this inflection point again is where my derivative is equal to 0. Continuing on, let's finish off over here. It looks like we're still being pulled downwards here, but if we weren't continuing to be pulled downwards, then the graph should get more and more and more negative, but it's not. The graph gets negative, more and more negative for a while, meaning my slopes get more negative for a while, but then my slopes start tapering off. It means that we have another inflection point right here. Inflection point. Maybe I should label just for consistency. Here's my critical point as well, right here where the slope of the tangent line is 0. So notice the slopes of my tangent lines are all positive along here, but they go from increasing in positivity to decreasing in positivity. So let's break these pieces apart again. Notice our slopes are all positive through here, so that means that my first derivative is greater than 0. But for this portion of the graph, although they're positive, they're getting closer to 0, and they hit 0 right at that critical point. So that means our second derivative is less than 0. And then for this part of the graph where we have our asymptote, notice that our slopes, although it looks like our slope is getting close to 0, it is pretty flat. It is just a little bit positive. If it were exactly flat, it would be exactly along this asymptote, and I wanted to indicate that it's not exactly flat. It's just a little bit positively sloped. So for this whole region, our graph is a little bit positive in slope, and that slope is increasing in positivity, meaning I'm getting steeper and steeper as I travel along this direction of the graph, meaning that my second derivative is greater than 0. So that was sort of a lengthy analysis of this graph, but I think it ties together the different shapes of the graph with a possible example of what those pieces would look like. I'm going to finish by defining some formal definitions of things that we've already said, just to tie things together for formality's sake. So, like we discussed, we said that our function f has an inflection point if my second derivative is equal to 0. And it turns out there are 3 different cases of this, and we'll look at example and then talk about those cases. Well, maybe I should talk about the cases. Well, yeah, we'll look at the example first. So we want to find the inflection points of f of x equals x to the 4th. So algebraically, that's pretty straightforward. We're going to find where the second derivative is equal to 0. So to do that, let's take the first derivative. This is an easy derivative to take. It's just power rule, so I end up with 4x cubed. And now I'm going to take the second derivative. Again, using power rule, the 3 comes down and multiplies by the 4, so I end up with 12x squared. And I want to know, when is my second derivative equal to 0? So I set this function equal to 0. 0 is equal to 12x squared. I can divide both sides by 12. I get 0/12 on this side, which is still 0. And I can take the square root of both sides, and I find out that I only have one inflection point, and that's where x is equal to 0. Maybe you did that in your head, but I'm going to do it on paper. So what does that mean? Let's take a look at the graph of f of x equals x to the 4th. I can bust out a calculator. Really, it looks a lot like an x squared function, but it's a little bit flatter at the bottom. Let's see. So I want to go to y equals, and I want to set y equal to x to the 4th, and then I'm going to graph that. So notice, yeah, on this calculator it looks exactly like a parabola. It's not. It's a little bit more squished at the bottom than a parabola. It looks something like that. So this type of inflection point is different than the inflection points that we saw on our graphical analysis, right? So back here we saw inflection points are where my second derivative are equal to 0, and these were places where my concave down shifted to concave up. That's one type of inflection point. Another type of inflection point is one that's just sort of a dud, that although our second derivative is equal to 0, this is also a critical point, and it's also the global min of this graph. And just by doing the second derivative and setting it equal to 0, that doesn't necessarily tell us whether that inflection point is going to be one of these cool inflection points where the concavity changes, or whether it's going to be one of these boring inflection points where it's just sort of a dud because the critical point is the same place as the inflection point. Finally, there's another definition that I used when talking about the graph, is the idea of a transition point. Transition points are just critical points and inflection points. So when analyzing a graph, all of the important points on this graph, here's a transition point, a transition point, and a transition point, and a transition, because it transitions between the different shapes of the graph. Finally, I'm going to end with the second derivative test and talk about what this is actually saying. So the second derivative test in formal language says, let C be a critical point of f of x, and recall a critical point. Critical points are the places where my first derivative is equal to 0. So that's where my tangent line is 0, or it's where the first derivative doesn't exist. These are the places that could be considered max and min values, although they might be a dud as well. So we're going to start with a critical point, and we're going to try to tell whether that critical point is a max or a min by taking the second derivative. We say that if the second derivative exists, and the second derivative is greater than 0, then that critical point is a local min. If our second derivative is less than 0, then our critical point is a local max. And if our critical point is exactly equal to 0, the second derivative is equal to 0, it's also an inflection point. It could be a max, it could be a min, it could be a dud. We don't really know. We're actually going to have to look at the graph in order to be able to figure this out, or do other types of analyses. What is the second derivative test saying? You could memorize this, but I think it's much better to just think about a picture. So, for example, let's draw a picture of what it means for our second derivative to be greater than 0. That means it's being pulled upwards. Here's my f prime of c is greater than 0. So our graph is being pulled upwards. Here's our point c, because it's our critical point where our derivative was equal to 0. And just by drawing those two pieces, we can easily see that that means that this critical point C is a local min, because it's at the bottom of this cup that's being pulled upwards. Similarly, likewise, let's say that our second derivative at C is less than 0, meaning that we're being pulled downwards. Our critical point C is going to be where the derivative is equal to 0. And it's easy to see from this picture that this is a local max. I don't have to memorize anything. I just have to know that being pulled downwards, the second derivative being less than 0, is going to give me my critical point is going to be top of that little hill. But, like we said, if our second derivative is equal to 0, you're tempted to say that it will always be the case that, like, here's an example of a place where my second derivative is equal to 0, and my first derivative is equal to 0. This is my critical point at C, where I have a horizontal tangent line, and my concavity is going from negative, here I'm being pulled downwards, to positive, I'm being pulled upwards. And this isn't a max or a min, it's just sort of a dud. But that's why I did the other example of the x to the fourth function. That's a bad picture. Here, that looks a little better. This is one where our second derivative is also equal to 0, and our first derivative is equal to 0. It's this flat part at the bottom, but it happens to be a min. So a second derivative being exactly equal to 0 is not conclusive for our second derivative test.